Welcome to this video, Year 10s. It's going to be about simultaneous linear equations, and in particular one method of solving them, which is via substitution. So simultaneous linear equations, what that actually means is we've got two straight lines, and as you can see in this first example, I've got two equations for those straight lines. And what we mean when we say solve them simultaneously is we're finding the value of x and y that works for both equations. Graphically, what this means is when you graph those two equations, where do those two equations meet? So what is the coordinate of something called their point of intersection? Now, I am going to demonstrate to you what I mean by this with these two equations. But before I do that, I will make a point that two equations or two lines, they'll always meet except for two particular conditions. Of course, if they are parallel, so what I'll say here is that they will meet or they will intersect. Once I get this working again. The two lines will intersect provided they are not parallel. Sorry, this is a bit of a slow process, as you can see. It doesn't particularly like me at the moment, this little thing. They will intersect unless parallel, and there is another case, well, it's not really the same thing, but there is another case that we need to consider, and that's if the two lines are actually the same line, because then we're not actually going to have one solution, we're not going to have one point of intersection, we'd actually have an infinite number of points where the lines intersect. So the two lines will intersect unless they are parallel. Now, of course, parallel lines will have the same gradient, so you'll know if they're parallel. You'll be able to tell from looking at their equations or from rearranging and checking what the gradient is. The other point I'll make, so they'll intersect unless parallel, and then if they coincide, so that's what I meant by if they are actually the same line. So if they coincide, you actually have infinite solutions. So you don't have cases that we'll need to be aware of just in case. And that's something that I'll have a look at in our next video, where I look at a different method of solving. All right, so just nice and simple, nice and straightforward to begin with. We've got two lines here, and when I say that we're solving them simultaneously, like I said, we're looking for where they meet. So with this example, what I wanted to do was just show you, if we were to say just graph these. So the first one, y equals x plus 2. So that is passing through at y equals 2. That's the y-intercept. Of course, if we've got that equation there and I want to know where it passes through the x axis, so what the x-intercept is, I would of course say this, equate it to 0, and then that means that x would obviously be negative 2. So yeah. So what I'm doing here is I'm just graphing this just so you can see graphically what's going on. And it's a little bit tricky, actually. It's not going to be exactly on there. It's a bit of guesswork for me, sorry. Might just go like this and then extend it out. So there's our straight line, almost straight line. All right, so there's our first one. Now, of course, I can do this with the second line. Might just do that on this side to keep them separate. So this was my rule, y equals 6 minus x. Y-intercept in this case is 6. I can read that from the rule there. You can see also that it's got a negative gradient, so it's going to come down this way. I want to know where it touches the x-axis, so substitute a y value of 0, and of course I can see that the x-intercept must be 6. Alright, so there we go. Might just do this one in a different colour. So there it is there. Okay, I'll label this, so y equals 6 minus x, and the other one was y equals x plus 2. So as you can see, the lines do meet because they're not parallel. One had a positive gradient of 1, the other had a negative gradient of 1. Okay, so what we can see here is, I mean, this isn't drawn perfectly to scale, but we can see that the lines do in fact meet. It's happening around about x is 2 and around about y is 4. Now that I've just approximated looking at my graph there, if I had a perfect, if I used graph paper and I graphed these perfectly to scale, I would be able to see that the point of intersection is 2, 4. So point of intersection, sometimes you can just write POI, point of intersection is 2, 4. Now what this means in terms of the two equations is this is a coordinate that works for both of my rules. So let's consider that. So my point was 2, 4. So x value of 2, y value of 4 means that 4 is equal to 2 plus 2, and of course that works. Let's check that coordinate, substitute it in for the other rule. If y is 4, then we have 4 equals 6 minus 2, which of course works as well. So when you are solving simultaneous equations, you do have a method of checking, and that is by substituting the x and y value into both rules should satisfy both of the equations. Now, the method I've just used here was just graphing them and having a look where the point of intersection is. Now, I've only done that so that you visually understand what the answer or what the solution to the simultaneous equations actually represents. I'm going to show you how we can get this answer. How do we get the x and y value of 2, 4 respectively just from these equations, so without graphing them at all? And that is to use this first method, which I'm going to show you, which is called substitution. So substitution is just one method, and it's it's a method that we've actually sort of used already. When we did our worded linear equations, we actually did this particular skill by substituting one rule into another and then solving. And by doing that, what we do is instead of having two unknowns, so instead of having an x and a y variable, by substituting one into another, we then eliminate one of the variables. We're left with one equation with one unknown, and we can then solve it from there. So I'm going to use the same equations that I had before and show you what I mean. First of all, when you are doing substitution, you always need either x or y to be the subject of the equation. So just one of your equations needs x or y to be the subject. Now, the ones that I've given you here, you can see y is the subject in both of these equations, so we can proceed. We can proceed without having to rearrange anything. So effectively what we're going to do here is you'll see that y is equal to x plus 2, but y is also equal to 6 minus x. So if I take this part, so 6 minus x, I know that that's what y is equal to, and I substitute that in for y in my other equation, you'll see I'm basically making these equal to each other. So you can see I'm having great difficulty getting my pen to work. There we go. So if y is equal to both of these things, it's equal to both x plus 2 and it's equal to 6 minus x, of course that means that x plus 2 has to equal 6 minus x. So that's one way to look at it. Another way, of course, is just if y is equal to 6 minus x, we can substitute it into this second rule here. So here is what I have. I can now solve this, of course. I could add x to both sides to begin with. So this would be x plus 2 plus x, so that's 2x plus 2. And of course now I can subtract 2 from both sides, so that leaves me with 4 on that side and 2x on this side. So x would be equal to 4 on 2. So x is equal to 2. So I've solved then for one of my coordinates, or one of my values that I need. Of course, when we are solving simultaneous equations, you're looking for an xy coordinate. So all I've got there is the x. I now need to solve for y. From here, if I know that x is equal to 2, I can then substitute that into either of these rules, and it should generate for me where each of those graphs are when x is equal to 2. What this x is equal to 2 is telling me is that the graphs both pass through x equals 2, and the y value at that point is going to be the same as well. So I'm just going to use this one. That means y is equal to 2 plus 2, which is 4. And as you can see, that's where we get that coordinate 2, 4. That is the solution. That is the to these simultaneous equations, and it is also another way of looking at it. It is the point of intersection. So point of intersection. Not going to write the whole thing. You can do that. It's a bit slow for me. Point of intersection slash solution to the simultaneous equations. And this is a very frustrating process, so I do apologise. Nope, I'm just going to say solution. Here's the solution to the simultaneous equations. Okay, so that is substitution in possibly its easiest form. Of course, you could come across some a little bit different to this, so I'll show you another one that's similar to this and then one that's a little bit different. Okay, so example B, we have 2x minus 1 and 3x plus 4. So again, first step would be just to check, do I have either x or y as the subject? Both of these have y as the subject like we had before. So what I can say is 3x plus 4 equals 2x minus 1. Okay, I will subtract 2x from both sides. The reason I'll do that is, of course, when I do 3x minus 2x, I'm left with just x. So that works really well. And then I'll subtract 4 from both sides. So that leaves me with negative 1 minus 4, negative 5. Okay, so now that I've got x is equal to negative 5, all I need to do is get my y value, my corresponding y value for that x value. Now it should be the same for both of my equations, provided I've solved correctly. So I'll do that with the top equation, and then we'll just do a little check as well on the one underneath. So y equals 2x minus 1. So let's get that y value. 2 by negative 5, so that's negative 10. Negative 10 take 1 will be negative 11. So our coordinate is negative 5, negative 11. So we'll check that for this second equation now. So 3 by negative 5, so that would be negative 15, plus 4 would give me negative 11. So it works for both equations, which is what you should always expect when you've solved accurately. So that's our solution to the simultaneous equations. Graphically, it's the point where the two lines meet. One more that looks slightly different, and that's this one here. In this equation, you'll see we don't have it in the form y equals mx plus b. We've got one equation that says x equals, and we have the other that says 2x minus 3y equals 7. All we need, like I said before, is one equation to be one equation to have x or y as the subject. Now we do have that. We've got x as the subject in this particular equation. So what I'm going to do is I'm going to substitute this bit here, so what x is equal to, for x in this second equation here. So what would that look like? Well, we need to do 2 times x. So we're going to do 2 times x, which is 2y minus 3. Notice you need to use a bracket here, because it's 2 times that number. That number we don't know, which is 2y minus 3. We then finish off the rest of the equation. So 2 times x minus 3y equals 7. And from here I can solve, because I've only got one variable, and that variable is y. I'll first expand. And then I'll collect like terms. So 4 minus the 3y is just y. And then I'll add 6 to both sides. So here I've got my y value in that particular coordinate. And now what I'll do is I'll get the x. Okay, so x is equal to 2y minus 3. So now that I know y, I can say that x is equal to 2 by 13. 3 is 26 minus the 3 is 23. So my solution, 13, 23. Now I can use this second one here just to check that. So if I do 2 by 13 minus 3 by 23, what I should get is 7. No, I've written that round the wrong way. I was just thinking, now that's not going to work. So what's gone wrong here? What I've done is I've reversed, so used to finding x first and y second, that I have reversed this coordinate. Hopefully you recognize the mistake before I did. 23 was actually my x coordinate and 13 was my y. So it should be written like this. And now this next part should make sense. So I'm doing 2 by 23, so that's 46, minus 3 by 13, so that's 39. 46 minus 39 is 7. So we've worked it out. It satisfies that second equation as it does the first equation here, which means that it is, in fact, the solution to the simultaneous equations. And of course, graphically, it's where the 2 lines would meet. So if I was to graph both of these lines here, I would find that they meet at this coordinate 23, 13. Okay, I'll leave it there. I will do a second video because I haven't shown you yet the other way that we can solve simultaneous equations. There's another way that's really useful when we've got equations in this form, like this one here, so the 2x minus 3y equals 7. If we have 2 equations that both resemble that particular form, so I guess like the general form, there is a better way rather than substitution to solve those. So I'll show you that in the next video.